Hi everyone, I'm Annie and this is Grace. And this summer we worked on graph algorithms and specifically probing and shortest path algorithms.
One application of shortest path routing is in traffic. Applications such as Google Maps use shortest path routing to figure out how to get from your starting point to your destination in the shortest amount of distance possible. So here the traffic network is represented as a graph, and we're given a distribution of edge lengths or the lengths of the roads. Because probing an edge or a certain road length is costly, we only have access to probability distribution. And we can use this to find the shortest path to some degree of certainty. So here we have a simple example of a shortest path problem. We're given two edges and S is our starting point and T is our destination. And so we have two possible paths. Each path only has one edge. The upper edge, E1, is either 1 or 3 with probability 1/2, and the lower edge, E2, is either 0 or 2 with probability 1/2. And so on the right, we have some questions that we ask ourselves when we're trying to figure out possible algorithms for shortest path routing. So the first one is, what's the probability that the upper edge is the shortest path from S to T? And so just looking at these numbers, we can tell right away that it's 1/4 when E1 is 1 and E2 is 0. And the second question is, if we probe the upper edge first and get 3, what's the probability that we have found the shortest path? So if we probe the upper edge and we get 3, then we know right away that E1 is the longer path because both of the possible values for E2, 0 or 2, are both smaller than 3. And finally, what edge should we probe to give us the highest probability of finding the shortest path with the fewest number of probes? The answer for this is the second edge, E2, because if we get 0 for E2, then we know right away that it's the shortest path. And if we get 2, then if E1 is 3, then we also have found the shortest path. So 3 out of 4 is the probability that we found the shortest path.
So now that we've set up the problem, we'd like to introduce this paper that's called Adaptive Probing Policies for Shortest Path Routing. And in this paper from 2020, they were looking at this problem, but specifically for the case where they have a graph just with n independent parallel edges from S to T. And again, the lengths of these edges are unknown, but we are given hints or predictions of the edge lengths from a collection of ML models. So we know the distributions for the edge lengths. And of course, we can find the true length of any edge or path by probing each edge, but probing each edge is very expensive, so we'd like to minimize the number of probes. And the question is that they were solving in this paper is, how can we find a nearly optimal path with high probability and minimize cost and number of probes? And so what they did in this paper was they chose a strongly adaptive submodular utility function. And we're going to define exactly what strongly adaptive submodular means in a later slide. But all you need to know here is that it's a utility function that measures the usefulness of probing an edge. And they show that using a greedy algorithm, they have this main result, theorem 2.1, which says that if you're maximizing a strongly adaptive submodular utility function, then this greedy strategy will succeed with parameters epsilon 3 delta, which means with at least 1 minus 3 delta probability, you will be within epsilon of the true shortest path. And the number of probes is bounded by a log factor times opt, which is the optimal number of probes possible through any probing algorithm. And so just to reiterate the case that they're considering in this paper, they were only looking at n parallel edges, which you can see here in the graph on the left side. And it's also illustrated in the two paths on the right side maps, because both of these are independent paths from the source 259 Amsterdam Avenue to the destination. And what we tried to do is extend this framework to general graphs, so not just limited to the parallel edge case. And so just to go back on that feature of the utility function that we had, submodularity is a property where probing additional edges cannot increase the conditional expected marginal benefit of an edge. So more simply, the expected gain from any particular edge cannot be higher if you want to probe it later. Essentially, it's a concept of diminishing returns of each edge. And so the first idea that we tried to tackle general graphs with was dynamic programming. And so we wanted to fold our probing algorithm into some kind of shortest path DP algorithm, such as Dijkstra's, for example. And so our error analysis showed that the errors would be fine. They wouldn't snowball or multiply. They would behave linearly. And so it would be simple enough to run the probing algorithm each iteration with parameters epsilon over n and delta over n. However, the problem that we were running into is that the number of probes needed was unclear, and we could not bound this. We could not upper bound this, even though we knew that it would be fairly accurate with high probability. So our second idea was, instead of using a DP algorithm, we would generalize their framework immediately to a general graph. And so to do this, we would need to find a similar utility function to theirs, but applicable to general graphs, which we could optimize greedily. And so for this utility function, we would need a succinct way of representing the probability that, given a subset of edges, the shortest path of the graph is not contained in this subset. We would need a way to represent this because the true probability does not fulfill the submodularity property. And so we tried many ideas, but overall, we always had the same underlying problem, which was that in order to know which paths are important to estimate the probability that we have a good or short path, although we don't need to calculate the probability distribution for every single path in the graph, we at least need to know what all the paths in the graph are, or consider all of them, so we can factor that into our estimation. And doing this would take exponential time, which is not reasonable for our solution. And to illustrate, we have this small counterexample here. To illustrate the problem with, to simplify our problem, we assume that we just have an oracle telling us the probability of each edge being contained in the shortest path. But even then, we still have a counterexample for why this would not work. And the main takeaway from this was that even by simplifying down to having an oracle telling us this probability, there's too much dependence between edges, even within a single path, because the outcome of one edge will determine how likely another edge is to be on the shortest path. And for their framework to work, we would need some degree of independence, which we don't have here.
So our third idea was to focus on the single path case. There's only one path from the source to the destination, and that path contains k independent edges. The probability distribution for each edge is given by a random variable, and our goal here is to find the probability that the sum of these random variables, or the total length of the path, is more or less than a given threshold theta with some degree delta of certainty. To apply the framework, we want to find a strongly adaptive submodular utility function so that we can apply a greedy probing algorithm. Intuitively, we want to probe the edges with higher variance first, because it seems like these edges would give us a better approximation of the sum. We proved that if we have two edges where the lengths of both edges are uniform random variables, then probing the edge with the higher variance first is better. In other words, the expected number of probes needed if the higher variance edge is probed first is less than the expected number of probes needed if we were to probe the lower variance edge first. However, we were unable to generalize this to cases where there are a large number of edges and they all have different distributions. So our next idea was to minimize the uncertainty. So our utility function is defined as the minimum of p sub k and 1 minus p sub k, where p sub k is the probability that the sum of the edges is greater than or equal to theta, given that we know the value of edge k. So our strategy here is to choose the edge that reduces uncertainty the most. However, we found that this utility function is not submodular. You can see the counterexample below. If x1 is 1 or 3 with probability 1/2, and edge 2 is 0 or 2 with probability 1/2. If we haven't probed any edges so far, the expected uncertainty of edge 2 is 1/4. However, if we suppose that we've already probed edge 1 and we know that edge 1 has length 1, then the expected uncertainty of edge 2 is 1/2. So here we have a gain in uncertainty, which proves that this function is not submodular. So knowing that using uncertainty as our utility function is not submodular, we looked at using the minimum uncertainty over all the edges we have seen so far. And so the strategy is the same. We choose the edge that reduces uncertainty the most. However, this utility function is submodular because at any given step, our uncertainty either decreases or stays the same. However, the order in which we probe edges has an effect on the minimum uncertainty seen so far. This is an issue because in order to implement a greedy probing strategy, we rely on the utility function to tell us in what order we should probe the edges. However, if the utility function returns different values based on the order that we probe it in, we can't find the optimal probing strategy. So next we used the fact that when we have a large number of random variables, the sum of the random variables approximates a Gaussian distribution. And so in this, for this, our utility function is the distance between the mean of the unprobed edges and the threshold. And so we can stop probing when we are at least delta confident that the sum is greater than the threshold. The problem that we had with this was that the mean and the threshold can decrease by the same amount. So the difference in distance always stays the same, no matter how many edges we probe. And so while this is submodular, it doesn't actually give us any useful information. We're currently reading a paper on submodularity by Golovin and Krauss in order to gain a better understanding of strong adaptive submodularity as it pertains to utility functions. Thank you for listening.